This video continues the discussion on observability. The previous video looked at definitions of observability using eigenvalue vector decompositions. Now, observability determines whether, using limited measurement information, and we say limited because often the output measurements have some form of subset of the states, can you identify all the values x of t? This video gives a test which is far easier to implement than using eigenvalue vector decompositions. Reminder then of what observability is. So a system is observable if it's possible to determine the value of the state x of t from available measurement data. Now, the available measurement data is usually the inputs and the outputs. So you can imagine you've got the inputs and the outputs over some time span, so y0 to yt, u0 to ut. So if you've got all this information about the inputs and the outputs, can you use that to determine what the underlying x of t is? The previous video showed that if you use an eigenvalue eigenvector decomposition, given as a equals w lambda v, then you could reduce the output equation to something of this form, and the key point is you notice that the eigenmodes z are mapped to the output through a matrix CW. And so it was clear that if CW has a 0 column, then the corresponding component of Z cannot be measured because it plays no part in the output measurement. A remark then: if a system is given in observable canonical form, it's always fully observable. So we shan't prove that, though it is relatively easy to prove, and you'll see that by the end of this particular video. What we're going to do here is define the concept of an observability matrix, because this is a convenient test of observability and it avoids the need for eigenvalue vector decompositions. This is a bit like the controllability matrix. In other words, it reduces to the rank. We need to do a rank test on a specified matrix. So the matrix takes a very simple form. Here you'll see the observability matrix is given by matrix C stacked over matrix CA all the way down to CA to the n minus 1, where n is the dimension of the A matrix. If this matrix M0 is full rank, the system is fully observable, which means that we can work out what all the states x of t are. You'll also notice that rank deficiency, so if this matrix M is rank deficient, then the rank deficiency equals the number of unobservable modes. The derivation of this is beyond what we want to do here, and you'll notice we gave a comment to this effect when we talked about controllability. So you can derive an identity a bit like this one here and follow some algebra, and you can show where this observability matrix comes from, but that's beyond basically the level or the depth that we want to go to in this video series. So remark: the formula I used to determine whether x of t can be estimated, and the key thing is can it be estimated? So the observability matrix gives you a yes/no, either x of t can be estimated or it can't, and you'll notice that is very different from saying how x of t is estimated. So the test doesn't tell you how, it just tells you can you. The latter topic will be covered in the next series, which looks at controllers and observers. Readers will also have noticed there's a strong connection between the observability and the controllability matrices. So here's the observability matrix. You'll see C, CA all the way down to CA to the n minus 1. And here's the controllability matrix, B, AB, A squared B, all the way up to A to the n minus 1b, and you'll see there's a very similar form here, so that in fact I can write that MO transposed is C transposed, A transposed, C transposed, A transpose squared, C transposed, and so on. And here you'll see there's a direct analogy now between these two expressions, and therefore the observability test is an equivalent to a controllability test on a dual system given as x dot equals A transposed x plus C transposed u. And you're reminded that the only thing we're ultimately testing is the rank. and therefore whether we do the rank of M0 or the rank of M0 transposed, you're going to get the same answer. Some numerical examples then of how to use this test. Here's the system. We've got an A, a B and a C. And all we do is form the observability matrix. So a reminder of what it is, it's C over CA, because here n equals 2, so we're going to have 2 block rows, and if I do those computations I get this matrix here. Now clearly that is full rank, and therefore this system is fully observable. However, what would happen if you change C to be 1, 1? Now, when I calculate the observability matrix, you'll notice I get this matrix here, 1, 2, 1, 2, and clearly this is rank deficient, because the 2 columns are the same, or the 2 rows are the same. The rank is only 1. So if I change C, I may no longer be observable, and that's a key point. Depending upon how you define your outputs, you may or may not be observable. Example 2. Again, you've got an A, B, C here, and our test is just form the observability matrix. Now the observability matrix given us C, CA, all the way down to CA to the N. Here we're going to go as far as CA squared, because this has got 3 states. So here I form it, there's my observability matrix, and what you'll notice is, if you're observant, is that this is rank deficient. And the reason I know it's rank deficient is the last column is the sum of the first 2 columns. So if you take the determinant of this M, then clearly you will get 0. A third example, and here I've basically used MATLAB because it's much quicker and easier, and you'll see I've defined the observability matrix here, C, CA, CA squared, and here's my matrix. And it may not be obvious to you, but if you look at it for a minute you'll see why it's obvious that this is clearly full rank. By doing suitable row column operations you can turn this into a triangular matrix. Now, fourth example is in observer canonical form, and you'll remember what we said earlier. If a system is in observer canonical form, we expect it always to be fully observable. So let's generate the observability matrix, and you'll notice it has a very particular structure. It's a triangular structure, and because it's triangular it must be full rank, and this is irrespective of the values A, B and C. So if you're in observable canonical form, then the observability matrix is always full rank, and therefore you're always fully observable. What about if you put a system in controllable canonical form? So here's one. You can see this A is in controllable canonical form. Now if I form the observability matrix, it's a bit of a mess, and you might say, oh, I can't see anything from here. But here's the key point. It's clear that the rank of this matrix, so this observability matrix, can vary depending upon the choices of A, B, C, D and F. So in other words, you could lose controllability even though we know, lose observability even though we know we're definitely controllable. And the reason is that you may be in non-minimal form. So a summary. We've introduced the concept of the observability matrix, and we've shown that here, if this observability matrix is full rank, then all the states are observable. We've given some numerical examples and shown that if you're in observable canonical form, the state space matrix is always fully observable. In general, computation of M0 and rank testing is tedious, so you're best to do it on a computer.